Okay, we have here on the board, there was an interesting suggestion made by Celkat on a similar integral, an integral in this form here, to do this separating the function into its odd and even parts, using odd-even decomposition. So instead of using that integral from that video, I can provide a link in the description, but this is the general form of the integral, where b is going to be some number, h is going to be an even function, g is an odd function in the exponent here, and we're going to have symmetric bounds around 0. And along with that, I give these definitions. This is just a definition actually of even and odd function. If we have an even function, h of x, it just kind of wipes out the minus sign. And if you have an odd function, well, the minus sign can just be brought outside of the function like we have here. So to get started with this, what I want to do is break this up into its odd and even parts using our formula for even-odd decomposition. Okay, we have our formula here for the even-odd decomposition. Now, if you just mess around with this and like distribute in the half and combine terms, you'll notice all this combines back to f of x as you'd expect. But the nice thing here is that we actually break this function, whatever it is, into its even and odd part. We want to do that with this because that's hopefully going to help us simplify this integral. So we can go ahead with this. Our f of x is just going to be this h of x, 1 plus b g of x. So then just plugging in values. So we're just going to use the same thing here for our f of x, but what I'm going to do is I'm just going to drop the function notation and just write this as h as a shorthand for the function, just to save a little bit of writing. So we'll write this as 1 plus b to the g. And then for f of minus x, we're going to use this definition over here. So plugging in h of minus x, we just get back h. Then here we're going to have 1 plus b minus g using this right here. Then for the second term, we'll use these same values, but we just have a minus sign between them. But now one thing I can do to simplify this term and this term is I'll just take this over to the side. And now if I multiply numerator and denominator by b to the g, well then this cancels and gives me a 1. This becomes b to the g. And then we can write this like this here. So let me just clean this up so we can see what's happening. So multiplying in like this, you'll see that now we have the same denominator here and here, which is going to allow us to simplify some terms. So now that we have common denominators, I'm just going to put these things together. So we'll still have our half out front. Now when I combine the numerators, I'm actually going to factor out an h. So we end up with 1 plus b to the g. And then we have that same thing in the denominator here. And then it's going to be a little bit different on this one. We'll still factor out the h, but we end up with 1 minus b to the g. And this is over 1 plus b to the g. But then here the 1 plus b to the g's cancel. And so here for our even part, we just have 1/2 h, that's nice. And now this part over here is odd. Now it doesn't necessarily look odd. How do we show that this is odd? Well, for our odd function, what I'm going to label this. We'll call it f(o) of x. So for this to be odd, that means that our f(o) of minus x needs to be minus f(o) of x. Well, let's see what happens when we plug a minus x in for everything. So this is going to become 1/2. Here we have h of minus x, but that's just going to be h of x. Then we'll have 1 minus b. I'm bringing back the full notation. So when we have g of minus x, I can write that, I can bring it using this, I can bring it outside, so we can write this as b to the minus g of x. Then here, the same thing in the denominator, we have 1b minus g of x. But we'll do that same trick again of multiplying by b to the g of x in the numerator and denominator. Then I think I'll continue down here. Let's see if there's enough space. So we'll have our 1/2 here. We'll have our h of x. This becomes b to the g of x, and this part's 1. We have minus 1 here, okay, and then we have 1 plus b to the g of x. But if I just multiply by minus 1 out front here, and I used to reverse the sign in here, just notice that this right here is the same as this right here. We just have added this minus sign. So this is actually our minus f of o of x, which is our definition of odd. So this here is an odd function. Okay, so now that we've broken our function into the even and odd part, and I've actually just broken into two separate integrals because we were adding the even and odd function together to represent this, so we haven't changed anything. And I just left this generic notation to represent this odd function just so I didn't have to write the whole thing out. And of course we can see this part's even just because h is an even function. But then at this point we can get more simplification just using the properties of odd and even functions. Okay, we have these two properties over here to the right. So for an even function, this fe of x, when we have symmetric bounds on this, we can just change our lower bound to 0 and bring a 2 out front. And then if we have an odd function with symmetric bounds around 0, we can just say the integral is 0. It's pretty easy to see these properties looking at a graph. You can just see the symmetry and how this works. But this is going to be pretty nice here because this is an odd function, and we just said that if we have an odd function with symmetric bounds, it's just 0. So this part's going away, and so that's just disappearing to 0. And then we can take this part that's an even function, and we can use this property. So we bring a 2 out front of the integral. We change this lower bound to 0, and so we still have our function half h of x. But of course we can cancel the 2 with 1/2, and what we've done is we've just reduced this kind of complicated expression all the way down to just integrating h of x from 0 to a. And so hopefully at the beginning of the problem, if h of x isn't too hard, we've got a pretty easy path to a solution here. Okay, it was a good suggestion by Celkat, and I thought it was interesting the way we could simplify this using odd and even functions. So that's it. We'll stop it there. Thanks everyone for watching. Have a great day.